Okay, so this is week Screencast 3, and let's just get into it because this is a quick video. This is more conceptual than solving. So basically, the first thing I'm going to do is explain what a direction field is. So this will make a little more sense to why this is useful. So what a direction field is it's illustrating the relationship between y prime of t, y of t, and then just t. Like all in a picture so that you can kind of see how the integral curves are behaving in a differential equation. So basically how you can approach them is you can either have a computer draw them or you can draw them. And so the first way you do it is that what most people do is they do it by hand. And so what you do is you have your equation, and then what you do is you set your right side equal to c, solve for y in respect to c, and then pick like 3 to 4 c values to test, and then you plot your field. So how you do that is you're looking at this equation, and right off the bat, most people can see that you're going to have issues with this equation at certain points, like when the whole thing will be 0 and it'll be just unhelpful. So usually what I do is I take note of those points because I'm like, those are going to be, like, I need to test around those because something whack is going on at them. So what I do then is based on just kind of like an intuitive know-how, I pick some points, and then I plug them into this equation to get a y prime. And then I'm plotting this as a y prime and a y, right? And then so, like I said before, since this is a relationship between a y prime, y of t, and t, your points are not going to be just points, they're going to be slopes, and like a repeating slope at one point. And so how this works is, like I said, you pick a y, like usually you pick around these, and then you plug it in, you get a slope, and then you kind of like loosely plot that slope. And then what you do is, and that becomes, you kind of see this picture taking shape of like these repeating integral curves, right? And that's basically what a direction field is. And so this is what it's like hand drawn, and this is what it is using GeoBra. So the next part of the equation is why is this picture useful to me besides just like seeing what I already know analytically. So with this, you can figure out critical solutions. And sometimes if an equation is too weird to solve analytically, you can solve it geometrically using a differential equation. So in this one, our critical solutions are those points that just don't make sense, like where the equation just becomes 0. So like I said, the definition of a critical point is at any point where y of prime equals 0. So immediately we know that's 0, 1, and 3. And so to do a qualitative analysis on a critical solution is you treat this where your critical points become where the line crosses the kind of like horizontal axis. And so then you loosely sketch in what that curve might look like, right? And so based on this, you've got, you figure out like what it's doing, right? Is it positive or is it negative? Is it above this line or is it below this line? Kind of thing, right? And so then after that, you have, okay, a critical solution, cool, I found them, what now? You have the types. The types here are you have a stable, unstable, or semi-stable solution. And to figure this out, it reminds me a lot of what you do in Calc 1, where you do these like derivative tests and you figure out if it's positive or negative. And based on that, you figure out like, is the function increasing or decreasing? It's a lot like that. So what you do is then you test, and then which I've kind of written here if you want to pause and read this. Just for time, I'm going to skip over it. Basically what you do is you test them, right, and you figure out if they're stable, unstable, and like all that cool stuff. And so for us, we have stable and unstable, and I'm pretty sure that one's unstable too. And so this is like a drawing of what these look like. So stable ones is where you have the integral curves are both converging toward this critical solution, which critical solutions end up looking like asymptotes usually. And so you have unstable where they're both diverging from it. They want to get away from it, and then the semi-stable where you have one side converging and one side diverging, like it can't decide. And so basically then what you can do is once you've kind of categorized and you've figured out analytically if they're stable, unstable, and semi-stable, how you illustrate that in your direction field geometrically is you have these arrows pointing to or from your critical points, right? And let me move myself over really quickly. And so basically for part D, so discussing limit behavior is basically these arrows, which you figure out your limit behavior analytically, you've drawn it in geometrically, and then now you just have to discuss what they mean, like what the arrows mean. And so basically, since you have 3 critical points, those define the regions, right? So you have a region from -infinity to 0, 0 to 1, and 1 to 3, and then 3 to infinity. And so I've written those all in, and then basically figuring out based on your analytical solution if they're positive or negative determines if it's increasing or decreasing, right? And then once you do this, since this is like a snapshot, this is like a smaller version of this graph, right? This is like a shorthand version of this graph, because these points then become asymptotes, and then based on what you're increasing or decreasing, which these arrows are, you can draw in your integral curves and know what direction they're going. And so then you have, this is the hand-drawn version, this is the GeoBra version again. And so, yeah, we've discussed limit behavior, find a critical solution, and done awesome, all that cool stuff. Thanks so much. I'm going to stop this.